Well, my dear students, Namaste. The next part of the unit factorization domain, uh, we start from the theorem. If D is U of D, then dx is a U of D. So its proof is here. Um, so fx be a non-zero and non-unit polynomial in dx, we have to show that it's it has a unique factorization. So then we have to show that number one, f can be expressed as b1 dot bs p1 x p2x all are in multiplication into pmx, where bi's are irreducible in d and pix are irreducible in dx. You know from the previous discussion that every polynomial is either it is primitive polynomial or it can be written as a unit element into a primitive polynomial. Okay, product of okay, this one, a constant and a primitive polynomial unit as irreducibles as and primitive polynomial. Next one, if fx equal to b1 dot bs p1x into p2x dot pmx, and again it can be expressed as c1 into c2 into ct into q1x dot qnx, where bi's and ci's are irreducibles in d and pix and qix are irreducible in dx, then s equal to t and m equal to n and bi equal to ci, that means where di and di are units in dx, that means bi and ci are associates. Pix equal to Rix into Qix, where Rix is a unit in dx, that means Pix and Qx are associates. So its proof is so I'm going to forward in step by step. Let fx be a non-zero non-unit polynomial in dx. We take it first. Again, I'm repeating it. If degree of x equal to 0, then fx is constant, and so it is in D. And if D is U of D, so the result follows immediately, because then fx can be written some irreducibles, each of degree 0. Also, you note that every fx, it is either an element of D or it can be an element of dx. Okay. Now let degree fx greater than 0 b denote the content of fx, minded content. That means its GCD of the coefficients become is called the content. So let b equal to b1 up to bs be the product of irreducibles in D. That means b, which is the GCD of the coefficient, can be written as the product of irreducible. That means if it is b is irreducible, then it's okay. If not, then it can be factorized into irreducibles. And it can be possible as b belonging to D, and so as D is D U of D. So then fx can be written as p1 b2 multiplication up to bs f1x, where f1x belonging to dx COD, and which is the primitive of fx. You note it. Every polynomial can be written as an element of d into a primitive of dx. So therefore, degree of fx and also degree of fx equal to degree of f1x, because b1 up to bx has a degree 0. Therefore, in order to keep equality, it must be degree of fx equal to degree of f1x. Now it is sufficient to show that a primitive polynomial fx of positive degree, primitive polynomial of fx of positive degree can be written as the product of irreducible polynomial of positive degree. Just we have to factorize f1x into some uh, polynomials, and as we isolate the GCD of the coefficient of fx, so all the f1 and its factorization all are must be primitive polynomial. We prove it by induction on the degree of fx. So if degree of f1x fx equal to 1, then fx is already irreducible, and we are done, because fx can be written in this form, some x plus b type, x plus b type, and x plus b type polynomial cannot be factored back, because if you go for a factorization, you get a constant term and a 1 degree polynomial, and it is not the definition. And so from the definition of factorization, it cannot be possible for a irreducible polynomial. So therefore, it becomes then irreducible. Now suppose that every primitive polynomial of degree less than fx can be written as product of irreducible polynomials of positive degree. Okay, just in the, we apply induction here. Okay, so if fx irreducible, there is nothing to prove, because it can be factored. Otherwise, fx can be written as gx into hx, and so gx, degree of gx and hx must have degree less than that of the degree of, that is the degree of fx. And as gx and hx both are of degree less than the degree of fx, so we have from the induction that what is, by induction both gx and hx can be written as product of irreducible polynomial of positive degree. This is the beauty here. Product of irreducible polynomials of positive degree. Okay, clearly then fx is also such a product, because you see here gx can be written as the product of irreducible polynomials, hx also product of irreducible polynomials. Now just multiply them, so this gives a product of irreducible polynomials. Okay, so fx is also such a product. So it's clear. So therefore, fx can be written in the form of the product of irreducible polynomial. So for uniqueness, we just write two different expression for each of fx. So it remains to show that BIs are associate of CIs and PIX is associates of QIX. And also S equal to this T and this M equal to this N. Okay. So and BIs, CIs are all irreducibles, and it can be treated as the polynomial of degree 0. And PIX and QXs are all irreducible primitive polynomials of degree of positive degree. Now let B equal to B1, B2 dot dot PS and C equal to C1 dot dot CT. Since PXs and QXs are primitive, it follows from the Gauss lemma. That means product of, so previous discussion in unique factorization domain 1, I have discussed it, that in Gauss lemma, product of two primitive polynomials or product of primitive polynomials becomes again a primitive polynomial. Since Px's and Qx's are primitive, it follows from Gauss lemma that P1x into P2x dot dot Pmx are all, it is also primitive, and Q1x into Q2x in P1x is also a primitive. So both B and C must be associate. Both B and C must be associate, and each is a content of fx. Okay, so see here, this is a primitive polynomial, this is a primitive polynomial. So what does it mean? Just fill it. So this has this P1 up to PM, this in this product has no common factor. Here also Q1 up to Qnx has no common factor. Therefore, this factor and this factor must be the of either it is equal or it is just differ by a multiplication of unit. So this means B and C, we call B means B1 up to BS product, C means C1 up to CT product. So therefore BC must be associate and it is a content of fx. Okay. Thus from the definition of UFD, what is it? In UFD, B1 up to BS, that is in associates of C1 up to CT. This means S must be T and Bi equal to some Di into Ci. So where Di is unit in D. Then from B1 up to Bs multiplication P1x into P2x dot Pmx, that is equal to so from this relation C1 into C2 dot Ct into Q1x into Q2x dot into Qnx. Just after cancelling, we just replace Bi by Di into Ci. Just we replace it here. What does it mean? This means D1, D2 dot ds so you see here, after cancelling Ci's, just put the value of Bi here, put the value of Bi here, and then cancelling this because they are units. Therefore, D1 up to dot ds, P1x dot Pmx equal to Q1x dot Qnx, all are in multiplication form. So what does it imply? Now viewing Px's and Qx's are elements of the corresponding field extension. Find it if in Z, then you can find it in Qx, because we have a little bit sense of division. I have to adopt it here. So therefore, in corresponding field extension. Fx. What does it mean? We know that why we consider field extension. We know every integral domain is either a field or it can be extended to a field. So therefore we take it px, ux are in dx, of course, but we can take it and another extension, which is field fx. Uh, it is called quotient field. Quotient means no. Quotient means it is it is like you see, if you see z, then you can think of the q. So if it is in zx, then you can think it in qx. So just looking in this form. So and px qx are irreducible. Px qx are irreducible. So then what we write? Pix divides Qix. Pix divides Qix. Here we give a division form of divisibility of a polynomial of polynomials by a polynomial. So we write P1x divides Q1x. How is it? You just go back to this relationship. So from here, put it d1 d2 ds p1x, just take a p1x from all these and equate and it is equal to q1 up to q1x. So this implies p1x divides 1 of q1x up to q1x. So therefore it is so it divides qix for some I less than s. Let qix be, just I renumbering it, qix be q1x. Okay, qix be q1x, suppose it is. Then q1x equal to u1 p1x. You can write it. As u1 p1x q1x are primitive, mind it. If these two are primitive, so what does it mean? You must be primitive. That means it must be a unit in D. It must be a unit in D. Mind it, it must be a unit in. Why? Because primitive means it has a GCD which is unity. Okay. So as GCD unity, so see here, Q1 equal to U1 P1x. So you know from a result of GCD, every divisor of, of, of GCD is the GCD or just an element. Every, say suppose A divides B, then AU also divides B, where you use unit. So every element has, suppose an irreducible element or say prime element has two types of divisors, is the element itself and one of its associates, just associates of the element. So every prime element is divisible by itself or its associates. So from this view, here each unit in D. Now I'm going forward. Then I just put Q1 x by U1 P1x, Q2 x by U2 P2x like this. So just put this value in the above relationship. We get above relationship means here this one, here this one. So here I put this value. We just put it here and get, what is it? d1 d2 ds and p1 up to p2 pm, q1 up to q1. So I just write it here again. So put it here. So I have d1 d2 ds. Just put the value of q1 by u1 p1x and cancelling p1. So we get d1 d2 ds p2x dot pmx here in right side u1 into q2x dot qnx. So repeat the above arguments successively and considering m less than n. So then from this relation, all p is exhausted, but some q remains. So after m step, we have d1 up to ds in left side, and in right side u1 up to um. Then the rest portion qm plus 1x dot qnx. So as LHS, here see this left hand side of this equality is uh, is a polynomial of degree 0, whereas right hand side is a polynomial of degree positive because q is from m plus 1, qm plus 1x, etc. Qm x are primitive polynomials, primitive non-zero degree uh, of non-zero degree, so primitive polynomials, so and non-zero degree. So it cannot be possible because here all are looking at constant 0 degree, and here are non-zero degree, so it cannot be possible. Therefore only possibility is m equal to n, because side by side we can prove such impossibility can again occur for m greater than n. Therefore m must be n. And so if m equal to n, then just put pi equal to ui qi for some ui, for some means ui is r units. Some it is better to left some are all units in the, then pix qx are irreducible because for uniqueness we have considered the different expression of the same fx, and there we say that pi's and qi's are all irreducible. So therefore pix equal to ui qix, as ui are units, therefore pix and qix are associates. Okay, so I am just point out again here the uniqueness means the unique just except up to the order of the vectors, but these are the actually associates. So in this sense we say these two expression becomes identical except the order of the factors or associates. So therefore such factorization is unique. Now we have some observation. Z is UFD. So from the above theorem we can say Zx is UFD. But if x equal to root over minus 5, it is not true at all. So why? Here is an example. Because 6 belonging to z root minus 5. Okay, 6 can be written as 2 into 3, and that can be again written as 1 plus root minus 5 to 1 minus root minus 5. Okay, this 6 has two types of expression, this one and this one, and more again saying that these are all 2, 3, 1 plus root minus 5, 1 minus root 5 minus 5. These are all irreducible elements. So therefore in z root minus 5 we get such element 6 which has two different type of factorization. So it's not so unique factorization. Therefore as z belonging to z root minus 5, but it has no unique factorization, Therefore, Z root minus 5 cannot be unique factorization domain. Here I just examine the irreducibility of 2, 3, 1 plus root minus 5, 1 minus root minus 5, which are in Z root minus 5. But procedure for proving each of them are same. Just we consider only 1 plus root minus 5. So you can prove for all other irreducibility. 2 and 3 are irreducible. You can easily know from your previous concept. So we consider only 1 plus root minus 5. I'm writing here for the others are similar. So irreducible means if this can be written as, these two has two factors, a plus root over 5b minus 5b and c plus root over minus 5 into d, abcd belonging to z. So just we have to prove it either is 1 or means first factor is 1 or the second factor becomes 1. So define a norm function from z root minus 5 to n union 0, you know it. This is a multiplicative norm function by n a plus b root minus 5, that is equal to a square plus 5b square. Then we have n 1 plus root minus 5. Just apply n here, multiplicative norm function. So it then multiplied in this form, this and again this. No. This one, multiplicative norm function. So here this n 1 plus root minus 5 means 1 plus 5, and here a square plus 5b square, c square plus 5d square multiplied by. So left side is 6 and right side by these two factors. So 6 can be written into 2 into 3, 1 into 6, or 6 into 1. So there are 4 possibilities. So a square plus sometimes a square plus 5b square equal to 1, c square plus 5b square becomes 6. You can write it, or one can write a square plus 5b square equal to 6 and 6 square plus 5d square equal to 1, or one can write a square plus 5d square equal to 3, 6 square plus 5d square equal to 2, and a square plus 5d square 5d square equal to 2, c square plus 5d square equal to 3. So one can write in 4 ways, you can get it. So for the case 1, you just calculate it and get a equal to 1, b equal to 0, c equal to 1, d equal to 1. So a plus root minus 5b becomes is then unit. Okay. And for case 2, c plus root over 5 minus 5 into d, that becomes unit. So from 3 and 2, we cannot get any such value of ABCD belonging to Z. So therefore, 1 plus root over minus 5 is irreducible in Z. Now you can check it by taking 46, the element 46, where 46 can be written as 2 into 23, and that can be written in this form. You can check it by taking 46 in the same, get the same conclusion. Now, like other PID also, here UFD, we have some results on common GCD. So in UFD, any two non-zero element have a common divisor. Here is a proof. A and B two non-zero element in GCD, UFD D. Then both are not units at a time. So we may consider the following cases. Let one of A and B, say A is unit, B is not unit. A is not unit, A is unit and B is not unit. So we can write it A inverse, then just an D, and A inverse equal to 1, which is the unity of D, and B can be written as A inverse B, and that is equal to A into B inverse, A into A inverse. Just take associative property, which shows that A divides B, and therefore A is a GCD of AB. If B is a unit and A is not unit, then similarly we can show that just in this way. Similarly, we can show that B divides A. Therefore, B here B divides A divides B, and again A divides A also. Therefore, A is the common divisor A and B. Here B is the common divisor of A and B. So we get common divisor of A and B. If AB are not both unit, then as in UFD, AB belonging to D, so the AB has some unique factorization. So let's write A equal to U into P1 whole to the power E1, P2 into whole to the power U2, PM power EM, and B can be written as B into P1 F1, P2 power F2 up to PM power FM, where UD are units in D, you can write it. So C be the common divisor of AB. So C must divide A and B, and you can write as C belonging to D. C has factorization Q1 power G1, Q2 power G2, and Qk power Gk be factorization by irreducibles. That means Q1, Q2, Qk are irreducibles. So each Qi divides C clearly from here. So just from here, Qi divides C. Again, C divides A and B. So therefore, each Qi divides A and B also. That means each Qi divides when it divides A. That means it divides sum of P1 up to P2 so this one. So so Qi must divides one of Pj. So Qi divides Pj, and again Qi divides B, again also some Pj. Okay, in particular, up to associates of the irreducible occurring in C must be a subset of the irreducible occurring in A and B. That means Q1 must divides some Pi, Q2 also, up to Qk also. But there is a question: sum of Pi may rest. Suppose it may be some of the irreducibles in A and B may remain not divisible by any of the Qk's. So there may occur in this form. So at least all of Qi's must divide sum of Pih. So you just note it. So therefore, from this sense, we are going to say that in particular, up to associates the irreducible occurring in C must be a subset of the irreducible occurring in A and B, and that's why the rest of the irreducible, some of the irreducibles in A and B may be not divisible by all of Qk. So therefore, the irreducibles in C must be a subset of the irreducible in A as well as B. Therefore, we write this one. Qi up to Qk, this is a subset of P1 up to Pa. Okay. Now similarly we can show that. So what is it? If it divides, then in order to divide A, surely all suppose Q1 divide P1, then G1 and the power of then the power of um, what is it? Then the power of P1 in A is E1, okay, or P1 is E1. So therefore, again, power of P1 in B is F1. Therefore, in order to divide Q1 to the power G1 to A and B, you must have to note that G1 must be equal to or less or equal to or less than the E1 as well as F1. Therefore, we can write G1 is less or equal to minimum of E1, F1. One can check it very simply. It's nothing tough to understand it. So we write it no, this one is not plus, but it is equal to. This one is not plus, but it is equal to. Okay. And what is the GCD? You can very easily, you can say that GCD is nothing but the minimum of EI, FI, because GCD is the greatest common divisor. So for you must have to take the equality for it. Observation. From this theorem gives a working principle to show an integral domain is not unique factorization domain. An integral domain is not unique factorization domain. Okay. So just to take an irreducible element and show that it is not prime. It is not prime. Okay. So because of this, because you know in integral domain, so what is it? What is it? In integral domain, every prime element are irreducible element, but in unique factorization level, every irreducible element is prime element. Okay, so an integral domain which not to be UFD, then you have to show that there is an irreducible element which is not prime. So from first theorem we can prove it. For example, in z root minus 5, it is not UFD. Z root minus 5, it is not UFD. Because you prove in another way that 6 has two different type of factorization, but using this GCD criteria, you can prove in this form, because in principal ideal domain, so any two element have a common divisor. So here 6 and 2 into 1 plus root minus 5 or 3 into 1 minus root 5 have no GCD, and that's why it is not UFT. So for proving this, just alpha equal to 6, beta equal to 3 into 1 minus root 5, 1 minus root over minus 5. So take this here we see 6 equal to 2 into 3, and that can be written in this form. And therefore 3 and 1 minus root over minus 5 are common divisor of alpha and beta. 3 and this one, because 6 can be written as 6 can be written as in this form. So common, okay, these are common divisor of alpha beta. Let d equal to, we write it here, be a common divisor of alpha beta for AB belonging to Z. So there exists CH belonging to Z root minus 5, such that C alpha equal to CD and beta equal to HD. So as from the definition of common divisor, define a function n. This it is this is norm function, and then it is okay multiplicative norm function. A multiplicative norm function, as it is multiplicative norm function, therefore we can write this. Okay, just for here, just take it, just apply an n function here. You get nd, as it is n alpha equal to nc into nd, therefore nd divides n alpha, and here nd divides n beta also. What is n alpha? 36, n beta means your 54. Then all possible values of nd divides 36 and 54 both, therefore the values of nd becomes 1, 2, 3, 6, 9, 18. Again d is GCD of 3 and 1 minus root over minus 5, therefore it is also, as d is GCD of this one, and 3 and this one, d is GCD of 3 and 1 minus root 5, and these are the common divisor of alpha and beta. See, 3 and 1 minus root over minus 5, these two are common divisor of d is the GCD, so d 3 and 1 minus root over minus 5 must divide d. So that again apply n function, that means norm function, then we get from here this 3 divides nd, n3 divides, and n of 1 minus root over minus 5 divides nd, that means 9 divides nd and 6 divides nd. So as nd has values 1, 2, 3 and 6, 9, 18, and 6, 9 and 6 both divides nd, so only the value we have rest for satisfying all these conditions is nd equal to 18. Now nd means a square plus 5b square, and that is equal to 18. And you can't any value v belonging to j is satisfying a square plus 5b square equal to 18, and therefore has no GCD of 6 and 3 into 1 minus root over minus 5. You cannot mix up with a common divisor, but you see it is GCD. Now we recall a theorem from principal ideal domain. In a principal ideal domain, if any two non-zero element A, B belong, have a GCD, say D, then D can be written as UA plus BB for some UB belonging to D. But if D is UFD but not PID, not PID, then we cannot, C cannot be expressed as C equal to AU plus BV, where C is the GCD of AU. So in PID it holds, but in UFD it cannot. Here is an example. Polynomial in ZX is UFD, and 1 is GCD of 2 and X, I write it. So for choosing such X, then one can be, if 1 is GCD of 2 and X, then we can write 1 can be in this form. 2fx plus xgx, where fx gx belong to zx. If fx equal to, just take this polynomial, gx takes the polynomial, then one can be written as 2a0, just compare this, you get. So this implies a0 equal to half. As fx belonging to zx, a0 must belong to z. But here we see a0 equal to half, that cannot belong to z. So one cannot be expressed as 2fx plus xgx for fg belonging to zx. So we just observe and remark something. Zx is UFT but not PID. Okay. So PID, the classical PID is a smaller class, smaller than the classical UFT. Okay. And as all are integral domains, so above all we have integral domain. So UFT is a subset of integral domain. Now we are in a position to find the inclusion, what I am telling you. Okay. So these are the results. This one here, this F is field integral domain, Euclidean domain. This is principal ideal domain, UFT and ID. So all theorems and results which are true in UFT. Okay, all results which are true in UFT is true in subsequent domain one. That means if it is holds in UFT, then it is in PID, then it is in FD, then it is in F. If it is PID, then it is ED, then it is A. Cannot say it is hold in UFT if it is in PID. So these results you can observe it, and with this words, there are so many questions may arise, so many discussion may also remain, but for looking for your syllabus, I am concluding this chapter and also lecture here. Thank you very much for listening me. Thank you.